The sixth decade brought a new focus to Dryden. In addition to atmospheric flight research, a series of space-related projects and unpiloted vehicle concepts were initiated. The Ames DC-8 and ER-2 airborne science aircraft were also transferred to Dryden in 1997, beginning a new era of Earth science research. F-18 Active Aeroelastic Wing, or AAW program, investigated the benefits of aerodynamically twisting flexible wings to improve roll maneuverability of high-performance aircraft at transonic and supersonic speeds.
3, 1. Complete.
This wing warping concept is similar to the technique the Wright brothers used on their early flyers. The F-18's wings were modified to increase their flexibility by replacing the wing covers with thinner ones. Leading-edge flap actuators were added to the wing to operate the outboard segments separately from the inboard segments. To accommodate these changes, the flight control computer software was modified. Conventional use of control surfaces at high speeds can result in unfavorable wing twisting and reduce control from a phenomena called aileron reversal. AAW used the outboard leading-edge flaps and existing ailerons to impart the aerodynamic force necessary to provide the desired roll force. AAW control technology can substantially increase control power and reduce aerodynamic drag and aircraft structural weight in future aircraft. A derivation of the self-repairing flight control system program a decade earlier, the Intelligent Flight Control System, or IFCS, flown on a highly modified F-15, incorporates the earlier program's self-learning concepts into flight control software. Using a neural network, it is capable of manipulating far more control surfaces at a faster rate than the first-generation self-repairing flight control system.
Neural nets are engaged. Clear for failure.
But IFCS technology is capable of more than simply making a damaged aircraft flyable. For example, intelligent flight controls could lead to rapid prototyping of aircraft control laws. The Autonomous Formation Flight, or AFF program, extended the symbiotic relationship of migrating birds by exploiting the performance benefits of aircraft formations. The traditional V formation allows all birds but the lead to reduce drag and conserve energy. Using differential GPS to guide AFF pilots into position, a NASA FA-18 flew in the wing upwash generated by a lead FA-18 and demonstrated a 14% fuel savings at cruise altitude, better than the project goal of 10%.
Strong effect right there. Started to roll the right slightly.
The Automated Aerial Refueling Project, AAR, an outgrowth of the Autonomous Formation Flight Program, evaluated the capability of an FA-18A aircraft as an in-flight refueling tanker for unmanned air vehicles. The project focused on developing accurate analytical models derived from actual flight test data to aid in development of an autonomous aerial refueling system.
Okay, this one's very smooth and it's not deviating left or right at all. Copy. The positive closure, a little low, coming up. She's got it.
The first ever autonomous probe and drogue airborne refueling operation was successfully performed on August 30th, 2006 by the Autonomous Airborne Refueling Demonstration, or AARD project.
Okay, we're in.
Pilots were on board the receiver FA-18 for safety purposes and to fly the aircraft to initial test conditions.
No, you need to come in another 10 feet.
A global positioning satellite-based relative navigation, coupled with an optical tracker, provided the precise positioning required to put a refueling probe into the center of a 32-inch basket dangling in the airstream behind an airborne tanker. As a testament to the autonomous system, Dryden pilot Dick Ewers and flight test engineer Marty Trout assumed a look-ma, no-hands position on the final refueling demonstration.
Okay, a nice smooth closure of the basket, slightly moving.
As important as the successful engagements, the system also identified and safely recovered from each missed attempt.
Okay, it detected a miss and came back on its own, so I did not do anything.
Projects like the AFF and AARD have helped to establish Dryden's leadership in autonomous aircraft development and flight research.
She's got it. She's got it.
And we have 5, 4, 3, 2, 1. Launch.
Required.
The X-38 prototypes mark the return of lifting bodies to the Dryden Flight Research Center.
10,000 feet.
Like the X-15 and previous lifting bodies, the prototypes were dropped from the center's venerable B-52B bomber. The X-38 Crew Return Vehicle, or CRV, was conceived as a lifeboat for the International Space Station. The X-38 was largely based on the X-24A, although its landing profile would differ significantly. Once the X-38 CRV had entered the atmosphere and slowed to subsonic speeds, it would deploy a large parafoil for landing. During flight tests guided by a GPS autopilot, the X-38 prototypes demonstrated precise touchdowns on the dry lake bed at Edwards Air Force Base. Research flights of the prototypes were conducted from 1998 through 2002, when the program was canceled due to changes in space policy. Other next-generation space vehicle demonstrators met a similar fate. The Lockheed Martin X-33 Venture Star was designed to research the flight characteristics of a full-scale reusable launch vehicle. The X-33 was a fully reusable single-stage-to-orbit vehicle that was to operate much like an airliner. The Orbital Sciences X-34 technology testbed vehicle was developed to demonstrate key technologies that could be integrated into the reusable launch vehicle program. Both programs were canceled in 2001 before either had a chance to fly. Research platforms of the early 1990s did not satisfy many of NASA's altitude and endurance requirements for Earth science missions. NASA created a program to mature the technologies necessary to seed the uninhabited air vehicle UAV industry and use this new generation of aircraft for high-risk experiments that were previously not feasible for manned missions. The program was called the Environmental Research Aircraft and Sensor Technology, ERAST. Two such aircraft were the turboprop-powered General Atomics Aeronautical Systems, Inc., Altair Predator B, and the piston engine-powered Aurora Flight Sciences Corp. Perseus B. Both of these ERAST aircraft were remotely piloted and designed to fly as high as 60,000 feet and on missions lasting up to 24 hours or more. Less conventional ERAST UAVs included the many solar-powered flying wings built by AeroVironment Inc. Pathfinder Plus and Helios prototypes were just two of these aircraft and were used for such missions as observing crops, monitoring shoreline, testing communications, and providing new sea detect and avoidance technologies which allows UAVs to steer clear of other aircraft.
Go ahead, NASA 2. We've been watching you bounce around 96.5 for quite a while now, and I think it's time to probably call it a record flight. Congratulations. I think it's time to turn around.
The Helios prototype achieved an ERAS goal by reaching an altitude of 96,863 feet in August 2001. As part of NASA's Airborne Science Program, Dryden used a modified DC-8 aircraft as a flying laboratory to collect data in support of experimental projects serving the worldwide scientific community. Originally based at the NASA Ames Research Center, the Airborne Science aircraft were moved to Dryden in 1997.
Okay, we're level at 250, stable at 420. Actually, we want to hold this altitude.
The DC-8 flies three primary types of missions: sensor development, satellite sensor verification, and basic research studies of the Earth's surface and atmosphere. The DC-8 has flown all over the world, allowing scientists to successfully address today's planetary issues, including global warming and deforestation. In 2006, the University of North Dakota began operating the DC-8 under contract to NASA. Dryden flies two Lockheed ER-2 Earth Resources research aircraft as high-altitude flying laboratories in the Suborbital Science Program under the agency's Science Mission Directorate. Like the DC-8, the ER-2s were moved to Dryden from Ames in 1997. The aircraft collect information about our surroundings, including Earth resources, celestial observations, atmospheric chemistry and dynamics, and oceanic processes. The aircraft also use electronic sensors for research and development, satellite calibration, and satellite data validation. Since the Airborne Science Program's inaugural flight on August 31, 1971, NASA U-2s and ER-2s have flown more than 4,500 data missions and test flights to support the scientific research endeavors of NASA, other federal agencies, states, universities, and the private sector. Since the late 1950s, the supersonic combustion ramjet has been seen as the means to achieve low-cost access to space and high-speed transportation. The scramjet can operate between Mach 5 and near orbital speeds. It is far more efficient than a rocket, as it burns oxygen from the atmosphere rather than having to carry its own supply. But while the potential of a scramjet is great, so are the engineering difficulties. After some 4 decades of study and ground research, the technology was ready for an actual flight of a scramjet-powered aircraft.
3, 2, 1, launch, launch, launch. Sequencer reset.
The X-43 made aviation history in March of 2004 with the first successful flight of a supersonic combustion ramjet or scramjet-powered airplane at hypersonic speeds, speeds greater than Mach 5 or 5 times the speed of sound. After being dropped at 40,000 feet from the B-52, the X-43 was accelerated up to near Mach 7 and 94,000 feet by a Pegasus booster.
Ready to set.
Ready to set.
Sep. Separation.
The X-43 then separated and operated its scramjet for approximately 11 seconds. During this time, the X-43 accelerated and achieved performance very close to the pre-flight predictions.
RV is stable at this time.
The next and final flight of the X-43A introduced greater unknowns. Unlike the previous flight, The scramjet engine could not be ground tested at Mach 10 for the complete burn because wind tunnels could only simulate those conditions for 1,000th of a second at a time. Computer analysis predicted that the aerodynamic heating at Mach 10 was twice that at Mach 7. For this flight, additional thermal protection in the form of reinforced carbon-carbon composite material had to be added to the leading edges of the X-43's vertical fins.
Launch on my mark.
In November 2004, the X-43A and Pegasus were dropped from the B-52. After being accelerated to Mach 9.6 and 109,000 feet altitude, the vehicles separated and the X-43A successfully sustained the desired cruise speed. Again, the flight data correlated well with pre-flight predictions.
The RV is stable at this time.
NASA Dryden remains the premier aeronautical flight research center of the nation, and not simply because of its location and accomplishments. Over the decades, with a can-do attitude, it has developed an extraordinarily knowledgeable workforce with diverse specialties. From subsonic to hypersonic aerodynamics, atmospheric to exoatmospheric physiology, powered and unpowered, as well as piloted and unpiloted aircraft. In the process, Dryden has pioneered a host of new technologies and methodologies related to aeronautics. Its engineers have been awarded patents and national research awards, and its pilots have been recognized with Collier and Harmon trophies. Just as important is Dryden's vast experience in developing and executing all manner of flight research programs, small and large, national and international, in-house or through partnerships. These are the attributes that continue to make Dryden the place to come for world-class flight research.